In this project, the compressible flow inside the bent pipe is simulated and the shock wave is investigated. 5 degree air enters through a pipe inlet with 0.9 Mach number. The extreme pressure gradient causes a shock wave. The mesh grid needs to be refined to capture flow ideally at high gradient zones. Therefore, we can hire the gradient adaptation option in ANSYS Fluent. The 3D geometry was generated in Design Modeler software. A bent pipe with a 3 cm diameter was sketched. In addition, an unstructured mesh grid was carried out using ANSYS meshing software, and overall, about 200,000 elements were generated. After hiring the gradient adaptation option, the mesh grid was refined and reached 1,450,000 elements. At the very beginning of the simulation, we should import the mesh file. So from File tab, follow Read, Mesh, and then look at the mesh file that you received with the other files and open it. There are several assumptions that need to be considered in this simulation. First, we use density-based solver type due to high Mach number. The pressure-based approach was developed for low-speed incompressible flows, while the density-based approach was mainly used for high-speed compressible flows. Secondly, we want to capture the behavior of the fluid over time. So by selecting transient simulation, variables are assumed to be function of time. And at last, we ignored the gravitational effects, so just left the gravity checkbox remain unchecked. For the next step, expand the model section and open energy. Since we wanna investigate temperature distribution at last, we should enable energy equation, so the solver will solve energy equation as well as flow equations. Then click on viscous bottom. In the appeared window, choose k-omega SSD model to solve our turbulent fluid equations. The SSD k-omega turbulence model is a two-equation eddy viscosity model which has become very popular. SST or shear stress transport is a comprehensive formulation which uses k-omega formulation in the inner parts of the band layer and switches to k-epsilon behavior in the free stream. As a result, it avoids the common k-omega problems. In the next step, we should define the working fluid properties from material section. After expanding it, you can see that the software defined the air by default, so we just need to edit the properties. In appeared window, change the density type to ideal gas. So the gas law is as following. The density is a function of pressure and temperature. After that, we need to apply the defined material to the flow. Apply the air material to our domain. As the last step in setup part, we should define boundary conditions. The first boundary condition is inlet, and its type is pressure fulfilled. We have entered the Mach number 0.9 with the gauge pressure of 0, and also the turbulence intensity equals 5% and turbulence viscosity ratio is 10. In thermal tab, we define the temperature as 278.15 Kelvin. At the outlet, we've got another pressure fulfilled type boundary condition with the same Mach number, but here's the point. The pipe at the outlet has an angle of about 38 degrees with the x-axis, so x component of direction is cosine of this angle and y component is the sine of it. The turbulence intensity and turbulence viscosity ratio is just the same as inlet. Also, the temperature is 278.15 Kelvin. As the last boundary condition, here is a wall with no slip shear condition and also it's stationary. Its thermal condition defined as heat flux of 0, so it's an adiabatic wall. The density-based solver in ANSYS Fluent solves the governing equation of continuity, momentum, and energy, if needed, simultaneously as a set of equations. Two algorithms are available for solving the coupled set of equations: coupled explicit formulation and coupled implicit formulation. In addition, we hired second-order Aufwind for discretization because of its higher accuracy. To check the convergence of the solution, we almost always check the residual values, which will be discussed later, but it can't be a trustable criterion, so we define a parameter to monitor in each iteration from report definitions part. In a transient simulation, when the monitored parameter gets to a constant value, I mean the fluctuations decrease, we can say the simulation has converged. But choosing the parameter which we want to be monitored is essential and totally depend on project. For example, in this simulation, the pressure at the outlet of the pipe and also the Y plus on the wall is of the sense. As you may know, it is recommended that within using K omega SST model, the Y plus should be below 1 to avoid any possible errors. So I've defined an area weighted average of pressure at the outlet of the pipe and another one for Y plus of the wall. Now let's get back to residuals. After each iteration, the solver records the values, so the reported value in the console part represent the differences between two consecutive iterations. If the values get below this absolute criterion we define in this window, the calculations will stop. At last, before start the calculation, we need to set initial values from initialization part. By using hybrid initialization, the initial values will be computed from all cells of domain. The time step size is 1 powered by -5 and max iterations per time step is 30. As you can see, the solution has converged, but here is a point. By reporting Y plus on the wall, it shows that the Y plus equals 37 and it's very high for K omega SST model. ANSYS Fluent provides an option to refine the mesh based on our defined criterion. From adaptation part, open manual, in cell registers drop-down list, make a new field variable. We want to define a criterion that allows the software to refine the mesh where the Y plus of the wall gets more than 1 and then refine it scaled by zone average. As shown in the console part, at first the cells were about 200,000 elements, but after adaptation it gets to 433,000. Furthermore, in this case, the pipe experiences a shock wave, so there is an extreme pressure gradient, and you can define another criterion, for example, solve the case in a steady state simulation and then determine where the gradient changes and the range of pressure. Then define a gradient adaptation for pressure in a specific range, and continue the simulation with the refined mesh. For post-processing, in order to create a contour vector path line in ANSYS Fluent, we should use graphics section in results part. But firstly, I need to create a plane at the middle of the geometry in XY direction. Define a plane in XY coordinates with the Z value of 0 to put it at the middle of the geometry. Now we can expand graphics part and make a contour. In the appeared window, we've got two main options. First, to select the desired variable from contours of field, and then select the surface, which means the surface that we want to create the contour on. In the appeared window, we've got two main options. First, to select the desired variable from contours of field, and then select the surface, which means the surface that we want to create the contour on. Once I choose velocity and plane 4, then here is the velocity distribution along the pipe. By changing the variable to pressure, I can have pressure distribution. There are many other options like Mach number, temperature, a streamline, and even Y+. Streamlines aren't available in 3D simulations, but our best option is to use path lines. I color the path lines with velocity and place them from inlet surface. As you can see, the path lines are very dense, so I use path escape to make it a little clearer. Air enters from pipe inlet with 0.9 Mach number and 5 Celsius temperature. The fluid experiences an extreme pressure drop at the bending zone. The mentioned phenomena is known as a shock wave and requires a high quality mesh grid to be simulated. The K-omega SST viscous model was used to capture fluid behavior perfectly, especially near the walls. On the other hand, the Y+ value is recommended to be under 1 value, but we've used a tetrahedron coarse mesh grid that couldn't satisfy that criterion. As a result, a gradient adaptation option was used to refine the mesh in zones with a high Y+ number. As shown in contours, pressure drops about 120 kilopascals during the pass and cause extreme variable distribution through the pipe. There is a direct correlation between density and pressure, as contours show. They experience an extreme reduction in values after bending zone, but velocity behavior is totally vice versa as expected.